All right, today's lesson is 8.2. We're looking at the Cartesian equation of a line. Now we know the Cartesian equation of a line. We've known it since grade 9. The standard form is ax plus by plus c equals 0. Today we're going to look at how to actually derive that from our vector equation of a line and how to go back and forth between the two. So we're going to look at a lot of similarities. All right, so let's start with the similarity of slope. So if you just take this line here, right, you can see the slope is rise over run, which would be b over a. That's our slope. Now if we write a direction vector parallel to that one there, notice that its direction vector has the coordinate a, b. So that's one thing to take note of. Now let's go down and look at this example here. I'm going to make this bigger. Here we go. So let's say we have some line L here, and we have a known point on the line, P naught, which has coordinates x naught and y naught, and we have an unknown point on the line P with some coordinates x, y. Now we can draw a normal vector, or a vector which is perpendicular to that line, and we can draw a direction vector which is parallel to that line. The direction vector we can figure out just using our slope equations. So our x-coordinate will be the difference between the x-coordinates in P and P naught, and the y-coordinate will be the difference between the y-coordinates, y and y naught. Now this normal vector, we're just going to give it the coordinates AB, capital AB, and that's going to be important for later, so keep an eye out for that. Now because these two vectors are perpendicular to each other, we can say their dot products equal 0. So when we solve for the dot product, which would be a times x minus x naught, and we can distribute the a into that and do the same with b. Rearranging a bit, we get ax plus by, and then we get this term here, these two terms. Now, both these terms are known because they're based on our known coordinates from the point P naught. So what I can do is I can just write that as one single constant that we call c. And now we have our equation ax plus by plus c equals 0. Now go back and notice that normal vector. In standard form then, it's very, very easy to determine what the normal vector or vector perpendicular is to our line, and that is AB. So you take the coefficient next to the x variable and the coefficient next to the y variable, and that's your coordinate. So let's try this with some examples here. First one is to determine the equivalent vector and parametric equations for this line. So in this line, we know a couple things. We know the slope, right? The slope m equals 3 over 4. And we also know, just remember that this is our y-intercept. So our y-intercept is the coordinate 0 and 2. So this can be a known point on the line. And if this is our slope, then we know that the direction vector m is equal to 4, 3. So now we can write the equation in vector form. R is 0, 2 plus some scalar quantity times 4, 3, where our scalar quantity t can be any real value. And then we can also write the parametric equations. I'll do that on the side here. So x equals to be 0 plus 4t, which I'll just write as 4t, and y equals 2 plus 3t. All right, let's try to do this the other way. So given the vector equation, in this case r equals 3 minus 6 plus s times minus 1 minus 4, where s is just a scalar quantity which can be any real value. And we're going to determine the equation, the Cartesian equation, in our slope y-intercept form. All right, well, from this we can see that is our direction vector. So I'm going to write m is minus 1 and 4. And so we know the slope then would be rise, so our change in y, divided by run, our change in x. So, sorry, that's minus 4. So we get minus 4 over minus 1, which just equals 4. So our slope is 4. Then we can actually use our slope equation. So if you remember slope equations, rise over run, or y minus y naught, or in grade 9 we wrote y2 minus y1, same thing, divided by x minus x naught equals 4, because we know the slope is 4. We also know a point on the line, our known point, y naught and x naught. So let's substitute our x and y coordinates for our known points into y naught and x naught. If we do that, we get y minus our y coordinate, minus 6, divided by x minus our x coordinate, 3. And that equals 4. All right, now we're just rearranging a bit. So we have y plus 6 equals 4 times x minus 3. Okay, I'll bring the 6 to the other side. I'm just going to do this over here because I've run out of space. So y equals, and distribute the 4, so we have 4x minus 12, and then we brought that 6 over, so minus 6. So our equation then is y equals 4x minus 18. Now a couple other points that I want to go over before we go on to our other example problems is if we have two lines, let's call this line 1 and this line 2, if their normal vectors are parallel, that means the lines are parallel. Why go through the trouble of finding normal vectors to see if they're parallel, determine the lines are parallel? Well, remember, it's really easy to find the normal vector. The normal vector you can pull right out of your equation from standard form. Similarly, if our two lines are perpendicular, then their normal vectors are also perpendicular, and hence their dot product will be 0. And we're going to use this in some of the example questions on the next page. All right, let's start with the first example. And there's actually two different methods we can use that I'll show you to do this question. So we have determined the Cartesian equation of the line passing through this point, which has some normal vector, 5, 3. Okay. Now what I'm going to do is I'm going to create another point on the line at some unknown location xy. Then I can find this vector AP, which will be a vector on the line, so a direction vector for the line, as x minus 4. So I'm just determining this position vector, x minus 4, and y minus negative 2, so a double negative, y plus 2. Now, since this is the normal vector, it is perpendicular to a direction vector. So I know that AP dot n will be 0. Their dot product is 0. So let's solve for their dot product. So we have 5 times x minus 4 plus 3 times y plus 2. And that equals 0. So now I'm just expanding and putting it into a standard form here. So we have 5x minus 20. So I'm just distributing here 3y plus 6 equals 0, or collecting like terms, And putting it into standard form, we get 3y plus 5x minus 14 equals 0. So that's one way of doing that. Let's call that method 1. Okay, there's another way of doing this though. Here's the other way. Since we know what that normal vector is, which is 5, 3, remember how easy it is to pull out a normal vector from the standard form of a line? So we know that the coefficient for y is 3, so it's going to be 3y. We know that the coefficient for x is 5, so plus 5x. We just don't know what that constant is. But since we know a point on the line, we can substitute those values, those x, y values in for x and y and solve for c. So we'll have 3. Our y value is -2 plus 5, where x value is 4 plus c equals 0. So now we just need to solve for c. So we get -6 plus 20 plus c equals 0, or c equals -14. Therefore, we know the equation of the line to be 3y plus 5x minus 14 equals 0. So that's another method. We'll call that method 2. Which method you prefer to use? Doesn't matter to me. You can use whichever one you like. Okay, next question. I'm going to do this on the side here, so this makes room. 1, show that these two lines, so we have two lines there, in standard form, are parallel and non-coincident. Coincident means that they lie one on top of the other. So this is saying the two lines are parallel, but separate, not on top of each other. All right, well, we can determine that they're parallel pretty easy if we just look at their normal vectors. So for line 1, the normal vector, let's call it n1, is going to be 3 and -4. Just our x and y coefficients there. For line 2, our normal vector, let's call it n2, it's going to be our coefficient 6 and -8. Now you can probably already see it with those two normal vectors. One is a scalar multiple of the other, so n2 is actually just 2 times n1. Because 3 times 2 is 6, minus 4 times 2 is -8. So if one is just a scalar multiple of another, then they're parallel. And since the normal vectors are both parallel, the lines are also parallel. So they're definitely parallel. The question is, are they non-coincident? For the lines to be coincident, then L1 would be able to be written as a scalar multiple of L2, the entire equation. You can see here that's not going to work. If we try and do twice n1, or sorry, twice of L1, well, here you'd get 3 times 2 is 6, minus 4 times 2 is -8, so far so good. But then the constant, minus 6 times 2 is -12, not +12. So in our case, that is not true. Therefore, the lines are not coincident. So they are parallel, but not coincident. All right, question number 2 says, for what values of k are the lines L3 and L4 perpendicular? Okay, well, if they're perpendicular, if the lines are perpendicular, then their normals are also perpendicular. And we can pull out their normals again right from those standard forms. So n3 is our coefficients k and 4. And n4 is our coefficients 3 and -2. Now, if they are perpendicular to each other, then we know n3 dot n4, their dot products will be 0. So let's find their dot products. Here you'll have multiply the x coordinates, so k times 3, we get 3k. Multiply the y coordinates, 4 times -2 minus 8 equals 0. Rearranging, you'll get k equals to 8 over 3. Okay, moving on to our last example. Our last example says determine the acute angle formed by the point of intersection created by the following pairs of lines. So we have two lines, and they're going to intersect, and we want to find that angle, or the acute angle, because there'll be an acute one and an obtuse one. We want to find the acute angle that is formed at that intersection point. Well, here are the direction vectors. So L1 has the direction vector, let's call it A. Doesn't matter what you call it. But the direction vector for L1 is -1 and 3. And the direction vector for L2, let's call it B, is 3 and 4. Now we don't really care where these lines are, because you can take two lines that intersect, and if you just want to know the angle, you can move those two lines anywhere you want. So really all we want to do is find the angle between those direction vectors. And to do that, we're going to use the geometric dot product and rearrange it to solve for theta. So we get cos theta equals the dot product with A and B divided by the magnitude of A times the magnitude of B. All right, so our dot product is -1 times 3, so that's -3. And then plus our y coordinates, 3 times 4, which is 12. And you need to remember to find the magnitude. We're using the Pythagorean theorem essentially. So the square root of -1 squared plus 3 squared square root of -1 squared plus 3 squared. And then the magnitude of b, which would be 3 squared plus 4 squared. Okay, simplifying a bit, this gives us 9 over 5 root 10. Remember, that's the cos of the angle, so take the inverse cos of both sides, and we'll get the angle to be 55.3 degrees. And we're all done.